Hello everyone, in this video I will go through the midterm solution. So I already posted the midterm solution in the Blackboard folder, so the same folder you submit your midterm exam. So you could print it out before you watch this video. So I would like to emphasize it's really important for you to fully understand the solution for the midterm, as even you did not do a good job in your midterm, it's fine, it's okay. So you really want to understand all the problems because you might see similar problems in your final exam. So you really want to watch this video and understand all the problems included in the midterm exam. So I have done part of the grading. So I haven't finished all the grading. There's too many questions for me to grade for this exam. So sorry for the delay. But you will not be able to see the grade right now. So I will post the grade immediately after I finish all the grading. So first of all, let's go through the solution. So the first problem is a typical problem to calculate CPI, computer performance. The most important two concepts for computer performance, one is CPI, one is the execution time for the CPU. So given that information, the execution time using machine A and B are both of them are 1 second. And then the clock cycle time is 1 nanosecond. So that actually means we will need 1 second divided by 1 nanosecond. And altogether, the number of clock cycles is 1e9, which is 10 to the ninth power, 10 to the ninth power. And then the number of instructions is also given. So for A is 1e9, for B is 1.5e9. So I think everybody understand what is scientific notation, right? If you don't understand what is scientific notation, what is 1e9, remember this is open book, open note, open internet exam. You can easily Google what is scientific notation for the number. So 1e9, what does that mean? It actually means 1 times 10 to the ninth power. So then you could calculate the CPI for A and B. And the second small problem asks you to calculate the execution time. And we would like to use the second most famous, the really famous computer performance equation number 2. So we have introduced the two separate computer equation performance equation, and you have used them in your first quiz as well. So I hope everybody understands this because you will also have similar problem in your final exam. So the instruction count, instruction number, multiply the CPI, multiply the cycle time, machine cycle time, and then we will have end up with the same time cost for A and B to execute this program. For A and B, you will end up with the same time. So they have the same speed. Which processor is faster? If they use the same amount of time, then of course they are same. Of course they are same. So problem C, I changed this number a little bit. Suppose the clock cycle time for A and B are different, and then you will just need to substitute different number for the CTA and the CTB, for the CTA and CTB, and then you will end up with the time, execution time using machine B. The execution time using machine B will be a bigger number, and you use the longer number divided by the shorter number, and you will have the speed up. So the longer number is CPU time B, the CPU time for B. It is twice longer than twice long as the CPU time for A. So of course, whichever has the shorter time is faster. So we'll say CPU A is 2 times faster than B. And then you use the longer time divided by the shorter time, and that will be your speed up. So 5 most important parts of a computer: computer input, computer output, the memory, the control unit, and data bus for a computer considered to be 5 most important parts of a computer. So we have this general concepts included in your slides. for a couple of times. So I hope everybody pay attention. So when we look at the computer, then of course we have the memory, the processor, and we have the input and output peripheral devices. But when you look at the central processing unit, the center part, which is the CPU, right? So when you look at the CPU, actually we have learned how to analyze the CPU. So what we did the data path of the CPU, right? And we try to analyze how each part they are connected to each other. For example, the control unit will send out all the control signals to control each piece of this circuit, and the data can be transferred from the register into the ALU to perform the calculation, and the ALU result can be transferred to the memory or can be put back into the register. So that's called data path. Right? And then the control unit send out all the control signals, connect to each pieces here, and that's called the control unit. That's called control unit, right? So the most important file parts of this whole computer, so why you have control unit and data path considered as two important parts here. It is a really important concept. So using the given computer to execute a program, how is the high-level code in translated into machine code, binary code? And there are some of you ask me this question when you work on your midterm exam, because some of you feel, oh, your question is not really clear. I mean, I really want to, as long as your answer makes sense, as long as you know the compiler, the assembler does help to compile the program, generate assembly code, and the assembly code will be translated to binary code. All we did in the whole semester is trying to use assembly code. But I really want to emphasize you should know the whole progress from the top level, high level code to the machine code. So even we do not write binary code, we do not write C code, we do not write Java code, we only write assembly code, but you should know which layer you are, right? So which layer we are actually working on. So this is why I ask this question. So as long as you list compiler, assembler here, then you will get the full credits. So I ask you to write down every step, list all the details, as many details as you know. However, this is just for you to review. So when I grade your problem, when I grade your answer, I actually, not grade all the detail. I just look for if you got the main idea or not. So for MIPS computer to execute assembly code, I want you to write down the binary code. And this is kind of like a trivial problem, not really. Some of you feel this is a little bit boring. And this question asked me to write down the binary code. And what's the meaning of that? Well, we assume we're in the machine. If you assume we're like the CPU, the machine try to generate the binary code, the CPU is actually reading the binary code. That's the only input to the CPU circuit, right? So we of course want to understand what's going on. What is the binary code? How the binary code is generated? So that's why I ask you to try to write the binary code by yourself for once, just for this problem. So the instruction I ask you to translate is ADDI, and I told you the operation code for ADDI is number 8, and the format for this problem is, the instruction format of given instruction should have the OP code for the first location, and that's the OP code, and we already call each tiny block here as a field, right? And I actually posted some reference material in Teams about this question when some of you asked me. So each block here is called a field. And there's a lot of examples, similar examples in the slides, similar to this one. So if you are still not familiar with this problem, you can check the Teams post. I posted maybe a week or a little bit more than a week ago. So you can check the post. And then check the slides examples. So we just need to figure out what is the value for RS, RT, and the immediate number. So that's the field value, which is decimal, And then we also need to figure out the machine code, which is binary, right? So of course, if you know what is number 8, binary representation of number 8 is of course 1000. And also remember that we need to spend 6 bits here. So look at this format here. So we need to spend 6 bits as the OP code to represent the OP code, and we need to spend 5 bits for RS, 5 bits for RT, and 16 bits for the immediate number. So I get 5 bits to represent RS, and what is RS? Source register, your input, right? So the ADDI, if you check the slides for MIPS assembly code, the very first time when we introduce MIPS assembly code instruction format, then we have like the reference sheet I gave you. For the first couple labs, you keep using that reference sheet, if you still remember. So that reference sheet has the general concepts for R-type, I-type, J-type instruction. And then for ADDI, which is the I-type instruction, so your RT is the destination, and your RS is your input, is your source, is your input register. So who is the input here? Of course, T2. Who is the output here? S3. So T2 is the input, S3 is the output. And then what is the binary? What is the index? Remember, each register has an index. So the index for T2 is number 10. The index for S3 is number 19. So all we need to do is fill in number 19, number 10, and the negative number 12, which is the immediate number, the only immediate number we have here in the field table. And then we also need to translate each number into binary. However, you need to be careful because we could only spend 5 bits. For each register's index. Right? So the RS has 5 bits here, 5 bits here. Look at this chart. So the 5 bits for each of the register index. So number 19, the binary version of number 19, and I have to only use 5 bits. So I think there's a typo here, so it should be 10011. So 5 bits, but I add one more. I actually add one more 0. Is there any way I can add the text? Oops. Okay, here. So it should be 10011. So which is the 5 bits representation for number 19. And I can add one more text here. So I need one more text, 5 bits representation for number 10. So what is number 10? 1010. And if you want to use 5 bits to represent number 10, then you will need to pad 1 extra 0 in the front. We need to pad 1 extra 0 in the front. So it should be 0110. So you add one more 0 here. So can I say something here? Correct. So corrected here. Oops. Yes, corrected here. So corrected to be so that's the 5 bits binary representation for 19, 5 bits binary representation for number 10. And the very last block here should be the binary representation for negative 12. And the interesting part is we all know how to write negative 12 because that's a negative number, so we will have to use 2's complement. So you will need to write the 12, the binary positive 12, and then you flip all the bits. You flip all the bits, and then you add it by 1, and this will be your negative 12, negative 12. However, remember, you have to make sure this is 16 bits long. This is 16 bits long. And then because you have 0, 1, 0, 0, the last 4 bits here is 0, 1, 0, 0. So you have to pad 12, 1 in the leading position, because this is a negative number. This is a negative number. A lot of you made a mistake because you didn't realize, oh, to make the negative number, I need to make sure all the leading positions are actually 1. So if you add some 0 here, then you change this number to be a positive number, and that would be wrong. And that would be wrong. Okay, so and the second problem after this is kind of like the hardest problem of this exam, and it could be still the hardest problem in your final exam as well, to be honest. So this is really important problem as we introduce the forwarding instruction reordering to solve the pipeline issue. So so how to analyze the pipeline, how to solve the pipeline problem, data hazards, control hazards is really important, a really important question. So you might keep seeing this in your final exam. So pay attention, 5-star for this problem. I know it is hard, it is confusing, but do the midterm is a good exercise for everybody. So let's first look at this problem. So what kind of data hazards can you find? So you have a load and ADD and ADDI, and the load and ADD and ADDI again. So when you look at this problem, actually there are quite a few hazards, data hazards in it. So first of all, we want to list all the. So let me save it as another file before I change anything. So first of all, I would like to list all the, so if I color this with blue, you see all the data dependency, and I have this blue register used again in the second instruction. And then in the third instruction, so in the second instruction, I have the T4, if I color it with the green color, and that's the input. However, it is output. However, it is used as an input again in the third instruction. So all those are considered, of course, as data dependency, right? So and then we have the register S0, which is the result we get from this load. And let me put it in blue color. And then unfortunately, it is used again as an input to inside of the fifth instruction, And then we have the S2 used in the fifth instruction. Unfortunately, it is used again as the input at the sixth instruction. So when you look at the color, then you will immediately see the relationship. So you have certain registers are generated from the previous instruction, and of course that kind of situation, it is called data dependency. It is called data dependency, right? So we have to list all the data dependency, because each of them will of course generate data hazards. So we have 1 to 2 as the first data hazard, and 2 to 3 second data hazard, 4 to 5 the fourth data hazard, and 5 to 6. So it's 1 and 2, 2 and 3, 4 and 5, 5 and 6. So many. So when I grade this problem, I know this is so challenging. The reason I put such a challenging problem here is try to help everybody understand this and get ready for your final exam. So as long as you figure out different types of data hazards, if you successfully detected and noticed the 1 and 2, 2 and 3, and you didn't notice 4 and 5, so even as long as you know what's going on in 1 and 2, then you actually should know what's going on in 4 and 5. And if you missed one of them, 2 of them, but you know most of them, and then you know the different types of them, then I still give you the full credit. So I was really nice grading this problem, but I just want you to know, you should understand this. This will not happen in your final. So when I grade your final exam, I will be really strict. So if you made any mistake, you may not lose a lot of points from this problem, but pay attention if you got the correct answer or not. So if you made some mistake, please try to understand the solution. Try to understand the solution, especially before final exam. So how many different types of data hazards can you find? And you want to list all of them. And of course, you could say in 1 and 2, 2 and 3, 3, 4 and 5, things like that. You can list the different types of data hazard, such as 1 and 2, 4 and 5, 2 and 3, 5 and 6. So some of them are load and use data hazard, load and use, such as 1 and 2. So your output, your final, you got the piece of data from the memory and you put it into register T0. So the result from the first instruction is actually T0, and it is used as an input to addition calculation in instruction 2. So the first instruction got a result T0, and it is used as an input to a calculation, instruction. Number 2 instruction is a calculation instruction. So we call this as this kind of data hazard as load and use data hazard, right? And the data hazard between 2 and 3, so you got the result of addition and you put the result into T2, and instruction 3 use T2 as an input, but it is still an addition calculation. So both 2 and 3, they're performing some general ALU calculation. So this kind of regular data hazard is not a load and use data hazard, it's just a regular data hazard. So the load and use data hazard is a little bit troublesome. So if you don't understand what is load and use data hazard, you really want to rewatch the video lectures about data hazards, okay? So that's really important. So for any load and use data hazard, because you have to go to the memory to get that piece of data, and you could not simply forward the ALU output to the ALU input into the next instruction, because you didn't actually get the result after your ALU execution. So you could only get the result at a really, really late time after you get access to the memory, which is actually the end of the fourth stage, in the 5-stage pipeline. So what can we do? And everybody should understand. So for a load and use data hazard, it will actually generate 2 bubbles, or let's say 2 stages, 2 pipeline stores. So it will stall the pipeline for 2 additional cycles. And suppose, so between 1 and 2, suppose we could do nothing. We cannot forward the result, and we cannot reorder the instruction. Then of course, between 1 and 2, you will have to pad 2 additional bubbles. And between same thing for between 4 and 5. So 4 is a load and 5 is a use. So load and use happens twice. So you will have 1 and 2 with 2 bubbles, and 4 and 5 with 2 bubbles in between them. 4 and 5, 2 bubbles. And then how about 2 and 3, 5 and 6? 2 and 3, 5 and 6. So for the general use ALU calculation, this kind of data hazard, it will if you cannot forward the ALU result to the ALU input, so we will have to have one pipeline stall, so one machine cycle pipeline stall, because you actually could generate the result after you finish the ALU calculation, and then you have to wait for one cycle to start the ALU calculation, because you will need to write it back to the register. So as we are not able to do forwarding. So that's why between 1 and 2, we will need to have 2 bubble, and 2 and 3 will have to add one bubble. And then 4 and 5 is a load and use again, so that will give me 2 bubble. And 5 and 6, that is ALU, so that will add one bubble. So altogether we have to add 6 bubbles. So we have to start the pipeline for 6 cycles, and that will actually cause the 6 additional machine cycle. And then suppose your pipeline is running in full speed. So how long time it should take? So remember that if the pipeline is running in a full speed, that actually means, suppose you can do forwarding, you can reorder the instruction, and then of course then your pipeline does not need to stall. There's no pipeline stall. And if there's no pipeline stall, then how long it will take? So suppose I draw a small, trying to make, can I make this thing really small? Oops. Give up. Let me just draw. So suppose I have a pipeline and I have to, so 1, 2, 3, 4, 5. So the pipeline is actually just stacking the different instructions. So if I have only 2 instructions, then it will look like this. If I have 3 instructions, then it will look like this. If I have 4 instructions, then it will look like this. If I have 5 instructions, it will look like this. And remember, we have how many? 6 instructions. So it will look like this. So how long time it actually takes? If your pipeline is in full speed? So you could even count. So there's 1, 2, 3, 4, 5 additional machine cycles, and plus the original 5 stage. So this will be 5 plus 5, which is actually 10 clock cycles if the pipeline is in full speed. So why it is number 10? So if you have a handle instruction, really you will not want to draw this figure, right? So, and then you could actually look at the how it is added, how the additional time are actually increased. So for each instruction, if I have only 2 instructions, then the overall time I actually need to add is 1 machine cycle. If I have 3 instructions, then the overall time I need to add is actually original stage number plus 2. And if I have n instruction, the total number of the instruction is n, then the overall time I have to add is actually n minus 1, right? The overall time I have to add is n minus 1. And then this is the way we could calculate the overall clock cycles cost for a full speed pipeline, because we're executing 6 instructions in total. So that's why this number is 5. So the shortest time for us to take is 10 clock cycles. So number 4, for a 10-stage pipeline, the branch hazard. So for the branch hazard problem, this is also really important. 5-star again. So 10-stage pipeline processor, the branch penalty. So if you forgot about how to calculate the branch penalty, so check. I actually posted this in Teams I actually posted this in Teams after I posted midterm exam. So there is one slide, one example in the slide, the last page of the branch hazard, branch prediction. When we talk about branch prediction, if you watch that video lecture, the very last part is working on the similar example. So I have a really similar example to this problem in the slide, and that's really important. And then I believe I put 5 stars in the note, in the video note. And I clearly told you, you will see this in your final exam. So check that out, okay? So, so if the branch could be resolved at the fourth stage, that actually means before the fourth stage, then you have to spend 3 stages, 3 clock cycles, to do some future job in advance. And before the fourth stage, there's no way for you to do anything. There's no way for you to know the result. So if you did something wrong because and you figure that out in the fourth stage, and then the 3 clock cycles before that are actually spent for nothing. So you have to redo everything. So that's called branch penalty, because that 3 clock cycles before the fourth stage actually has to be redo again. You have to redo those things again. So that's why 4 minus 1 will be the answer for this one. So if your branch can be resolved in the nth stage, and then the branch penalty is n-1 clock cycles, So suppose we know the ideal CPI for a branch pipeline processor is number 1, and this is given, okay? So this is given all the time, and you should know this as a common sense. So we introduced this in the slides as well. So the ideal CPI for a pipeline processor is number 1, and there's no data hazard, no structure hazard. That actually means there's only branch hazard. Okay? So to execute a given program, 40% of the instructions are branching instruction, and branch prediction accuracy is 60%. So that actually means 60% of the time your branch prediction is correct, and 40% of the time your branch penalty will need to be paid, because if you made a wrong prediction, then you need to pay the penalty. However, you do not make a wrong prediction every time. So only 40% of your branching instruction had a wrong prediction. However, not all the instructions are branching instructions. So how many of them are branching instruction? Only 40%. So for every one instruction, in average, you have 0.4 instruction. For every one instruction, you have 40% of it could be a branching instruction, And then within all the branching instruction, then we would like to know the accuracy of the branch prediction. So only at 40% rate, then we are doing a wrong prediction. So of course, not every time we're doing a wrong prediction. So the wrong prediction percentage is 1 minus the prediction accuracy. So 40% of the time, this is a branching instruction. And even it is a branching instruction, only 40% of the time of a branching instruction could be a wrong prediction. And only at the wrong prediction time, then you should pay a branch penalty. So you will have to spend 3 extra clock cycles only at that time. So then we have to, calculate the penalty with some weight on it. And what is the weight? Of course, the weight is generated by the branching percentage multiply the wrong prediction percentage. And then overall, it will be 1 plus this part. and then it will be 1.48 for final answer. So when I grade the exam, actually, as long as you have the formula correct, if you did a wrong calculation, then you still get the full credit. You still get the full credit. So I'm trying to be nice in the grading. So the last problem is a programming problem, and you could of course write this down in Mars simulator and try to test it, but I believe most of you actually didn't do that. So pay attention that you will still have programming problems in your final exam. So sometimes this kind of problem can cost you a little bit longer time. But you have already did quite a few different labs, so you should be well practiced. You should be well practiced. So you just need to be careful. If the user first user input was 8 and then print out correct and terminate the program. Otherwise, ask the user to type in a number again. And if the second input was 8, then you should print out correct. Otherwise, you should print out game over. So if you still remember, in your lab, I asked you to did a similar problem, but I told you, well, you can try some bonus question can be if you allow the user just to try limited amount of time, and which is this problem, right? So suppose I want the user to guess a number, but the user can only guess for twice, and then how can you control the loop? So everybody know how to ask a user to type in an input, and that is number 5 system call, and how to print out things that's number 4 system call. That's a number 4 system call, right? So after you get the user input in, you could save it into a certain register. And then what we did here is S1. So S1 is the user input. And I actually write down this so you cannot determine to use any other register because I put that part there. So you have to use S1 as the user input. And what you have to do is compare S1 with your true answer, If it is correct, then you should jump to the print program for printing the correct message. If it is wrong, then you should let the user to try again, right? If it is wrong, you actually should not stop right now. You have to let the user to try again. So if it is wrong, then you really need to loop back. You really need to go back to this label, because the loop check label actually is the starting point of ask a user to type in an input and then do the check. So however, remember that we have to control the whole loop. The whole loop can only be performed for two times. So there has to be one counter, such as a constant number 2 here. So I can use the constant number 2, and I can use index number like a counter variable, and I can add it by 1 each time and compare it by 2. And if it is already 2, then I will stop. Go to the next step. If it is not 2 yet, I will loop back. Branch back to the loop check. And then redo this again. Of course, then this will be only done for twice, right? So this is how you do this in a pretty neat way to finish this program. Some of you had some other version. As long as your whole program makes sense, then you get the full credit. And sometimes some of you did have some extra instructions. So you did have most of the part correct, but you put some extra and irrelevant instructions, which does not hurt. So you still get the basic thing right, but you add something extra, but that's fine. So if that's the case, you still got the full credit. So I'm trying to be nice for grading. Okay. So if you still have any question, let me know. So and that's for the midterm solution. make sure you watch this video. If you didn't have time this week, make sure you watch this video before final to get ready for the final exam. To know the midterm solution is beneficial for a final exam. All right, I'll stop here.